According to Karl Friston's free energy principle, FEP, the brain is essentially a prediction machine whose primary task is to predict the future. It accomplishes this by maintaining an internal model of the world and using that model to generate predictions. The brain continuously updates this model by comparing its predictions with the sensory information arriving from the outside world, then modifying the model accordingly. The updated model produces new predictions, which are refined again, and the process repeats continuously. In this theory, free energy is a mathematical quantity related to the error in our predictions. Put very simply, it is the quantity the brain tries to minimize in order to reduce the likelihood of surprise. Modern AI systems, such as deep neural networks, operate on a remarkably similar principle. A neural network is essentially a computer that is programmed through data. It has inputs and outputs. Initially, its parameters are random, and for each input we provide the desired output. The system calculates the error, similar to what the free energy principle calls free energy, and then adjusts its parameters using a method known as gradient descent. Our brains do not literally run the same algorithms as today's neural networks, but many theories, including the free energy principle, describe learning as a process similar to gradient descent on an internal error or energy function. Because this error minimization often takes place in a fraction of a second, we rarely notice it consciously. There are, however, situations where we can catch the process in action. Most of us have experienced listening to a song without understanding the lyrics. Then we read the lyrics, listen to the song again, and suddenly every word becomes perfectly clear. The song itself has not changed, yet it has become understandable. This happens because what we hear is only partly determined by the sound entering our ears. A large part of the experience is supplied by the brain, based on its internal model. When you read the lyrics, your brain updates its internal model, and the incoming sounds suddenly make sense. The acoustic signal has not changed, only your perception has. From that point on, you recognize the words much more easily, simply because your mental model has learned what to listen for. Another classic example is the Necker cube, a simple two-dimensional drawing of a three-dimensional cube. Because our brains are accustomed to interpreting 2D projections, we immediately perceive it as a three-dimensional object. The catch is that this projection can represent two different cubes. In one interpretation, the square on the right appears farther away, and the one on the left is closer. In the other, the opposite is true. With a little concentration, we can force ourselves to see either version. We can even switch back and forth between them, and during the brief moment of transition, the image doesn't seem to represent a three-dimensional cube at all. In other words, with a little effort, we can consciously switch between different mental models. Visual illusions work in much the same way. At first, we see one thing, but once the trick is revealed, our interpretation changes. Here, too, we can observe the process as it unfolds. In the case of the Necker cube, the brain initially maintains two equally plausible predictions, one in which we see the cube from the left, and another in which we see it from the right. Our conscious experience is not firmly committed to either one, but as soon as one prediction becomes slightly stronger, our mental model locks onto it, and that interpretation becomes our perceived reality. In a sense, this process resembles wave function collapse in quantum mechanics. For a while, the two possible cubes exist in a kind of superposition within our minds until our mental model, the brain's internal representation of the external world, suddenly collapses into a single, well-defined state. The fact that the brain functions as a prediction machine provides an obvious evolutionary advantage. Survival often depends on how well we can predict the future. Imagine walking through a forest where predators may be hiding. If a bush suddenly rustles, the wise response is to run, because a tiger might leap out the very next moment.
If we were unable to predict what was about to happen, we would only become aware of the tiger once it was already preparing to attack, and by then, it would be too late. Animals that cannot predict the future simply do not survive for long in the course of evolution.
But a mental model is useful for far more than simply avoiding predators. Beyond a certain level of complexity, almost everything we do depends on it. A mouse, for example, could never find its way back to its nest if it did not maintain an internal map of its surroundings. Animals without such a model of reality would wander around almost randomly, hoping to stumble upon food before becoming food themselves. This kind of behavior is found only in the simplest forms of life. We humans possess remarkably sophisticated mental models and predictive abilities. We rely on them to make decisions and to plan our actions before they are ever translated into muscle movements. In a sense, we live inside our own internal reality, or, stated even more strongly, the reality we experience exists only within our minds. That may sound strange at first, but it is actually quite easy to see why. Our senses are extremely limited. At any given moment, they provide us with only a tiny fraction of reality. Yet when we stand in the middle of a room and look straight ahead, we still know what is beside us, behind us, or even in the next room, and we make decisions accordingly. Imagine if you could rely only on what you sensed at this exact instant. It would be as if you could see the world only through two tiny holes, your eyes, while being unable to use your mental model, or in other words, your memories. We could even simulate such a memoryless state. If you turned your head away and then looked back, the scene would be completely different from before. The world would change chaotically whenever you were not looking at it. But that is not the reality we experience. The world appears stable and predictable, and that stability is made possible by the way our brains work and by the mental model they construct. What our eyes actually see is nothing more than raw sensory data. What we truly experience is the model of reality that our brain builds for us. This is so fundamental that even when we look at a photograph, we do not see exactly what our eyes are detecting. Our eyes constantly scan the image. Much of the incoming visual information is blurred or out of focus, and it is filled with visual noise, such as the fine network of blood vessels spread across the retina. Yet despite all of this, we perceive a sharp and coherent picture. That picture is constructed by our brain. In fact, a large part of perception itself is prediction. The brain does not merely predict the future, it also predicts, or more precisely, generates, our experience of the present. Another fascinating finding is that when we recall old memories, many of the same brain regions become active as when we imagine the future. This suggests that remembering is not like replaying a stored recording. Instead, the brain reconstructs the past from fragments of memory. In other words, the brain does not merely predict the future and generate the present, it also, in a sense, predicts the past. The reality you experience is not the external, objective world itself, but rather the mental model of that world created by your brain. According to neuroscientist Anil Seth, we spend our entire lives inside a kind of controlled hallucination. Based on incoming sensory information, the brain continuously constructs and updates an internal representation of reality. This hallucination is constantly constrained by signals from the external world, which is why it usually provides a remarkably accurate picture of our surroundings. Think about how astonishing that really is. Our brains, a roughly 2-kilogram organ inside our heads, contain a compressed model of the reality we experience, together with many of the rules that govern its behavior. Using this model, the brain runs an astonishingly accurate simulation. So accurate, in fact, that we usually notice immediately if something important in the world suddenly changes, or if the laws of physics appear to behave differently. If we ask ourselves how big a computer capable of simulating an entire world would have to be, the answer is surprisingly simple: roughly 2 kilograms. But what would happen if we simply connected human brains together? Instead of each participant receiving sensory input from the external world, their brains would receive the predictions generated by the other participants' brains. This is, of course, a highly speculative idea. We still do not understand the brain well enough to know whether such a system is even possible. Nevertheless, it does not seem entirely inconceivable that, by connecting multiple brains and synchronizing their controlled hallucinations, we could create a single, continuous, shared collective hallucination. Imagine 4 people lying in isolation tanks, completely cut off from all external sensory input. Now imagine that brain-computer interface technology has advanced to the point where we can directly connect human brains. We cannot be certain that such a system will ever be technologically feasible, but let us assume that it is. In this system, whatever one person's brain predicts is experienced as reality by the others, and vice versa. We could even add a computer to the network, one capable of generating artificial sensations that initiate or influence the collective hallucination. At first, the experiences of the participants would probably be chaotic. But because every brain constantly strives to build a coherent mental model, the system might eventually settle into an equilibrium in which all of the participants' mental models become synchronized. The way our minds construct mental models may be particularly well suited for keeping multiple participants synchronized. Perhaps a full-scale simulation of an entire physical universe would not be necessary at all. Maybe all we would need are the right connections between minds. As I mentioned earlier, we do not know whether it is actually possible to wire together human brains in this way. The answer is obviously unknown, since neither neuroscience nor technology has advanced anywhere near that far. However, there is a fascinating phenomenon that suggests such an idea may not be entirely impossible. One possible treatment for severe epilepsy is a surgical procedure called a corpus callosotomy, in which the corpus callosum, the bundle of nerve fibers connecting the brain's 2 hemispheres, is cut. This operation effectively separates the left and right hemispheres. In some patients, the result is a condition in which each hemisphere appears to possess its own independent consciousness. Researchers are able to study this phenomenon because the brain's right hemisphere controls the left side of the body, while the left hemisphere controls the right. This makes it possible to communicate with and test one hemisphere independently of the other. The condition is known as split brain syndrome, and it suggests that perhaps each of us contains 2 separate minds. Under normal circumstances, however, the corpus callosum links them together, allowing them to function as a single, unified consciousness. Jeff Hawkins takes this idea even further with his 1,000 brains theory. According to Hawkins, our minds are not composed of 2 independent systems, but of thousands of mini-brains. Their basic building blocks are cortical columns, each responsible for modeling a small part of reality. Together, these columns form a highly connected network. Ray Kurzweil describes a similar architecture in his book, How to Create a Mind. He refers to the basic building blocks as pattern recognizers, dynamic learning components, whose hierarchical cooperation forms the foundation of how the brain works. Donald Hoffman also envisions the mind as a hierarchical system. Notice that I deliberately said mind, not brain, because Hoffman approaches the problem in a very unconventional way. His central claim is that consciousness, not space, time, or matter, is the fundamental ingredient of reality. According to his theory, the brain is merely a representation of human consciousness. In other words, consciousness does not emerge from the brain. Rather, the brain emerges from consciousness. This is certainly a radical claim, but there is one very powerful argument in its favor. The only thing you can know with absolute certainty is your own existence and your own conscious experience. The existence of the physical world around us is, strictly speaking, only a very strong belief. After all, it is conceivable that we are nothing more than brains in a vat, with our reality being simulated by a computer. Nor can we be absolutely certain that other people are conscious, or even that they exist at all, because their subjective experiences are accessible only to them. From this perspective, it seems perfectly reasonable to take consciousness as the starting point and build our model of reality from there. In Hoffman's framework, the most fundamental unit of consciousness is the conscious agent. Through the hierarchical interactions of these conscious agents, he attempts to derive everything else: the laws of physics, quantum mechanics, relativity, and even the properties of elementary particles. My goal here is not to analyze these theories in depth or to argue for or against them. Rather, I simply want to point out that most models of the mind, or the brain, assume some kind of hierarchical structure. If we begin connecting individual minds together, we are essentially just adding new layers to that hierarchy. And if every mind were connected, the result would be a single, enormous mind. Such a mind would, in a sense, possess a massive split personality, because the individual would no longer occupy the top of the hierarchy, but would instead become just an intermediate layer. In this picture, what we call reality would simply be the interface through which individual minds interact with one another. This idea bears a striking resemblance to the God in Andy Weir's short story, The Egg. In the story, an ordinary man arrives in the afterlife and gradually realizes that, because reincarnation is independent of time and space, every human being who has ever lived on Earth is, in fact, himself. Could it be that we are already part of a single, vast, unified mind? Could this be a valid way of describing the reality we live in? And if so, might it explain our universe just as well as our current scientific models and theories? If these questions fascinate you, and you'd like to explore how relativity, quantum mechanics, consciousness, artificial intelligence, and the simulation hypothesis might fit together into a single, coherent worldview, you can download my book, Simulated Reality, completely free of charge. You'll find the download link in the video description. And if you enjoyed this video, please consider giving it a like and subscribing to the channel. It may seem like a small gesture, but it helps these videos reach more people who are interested in science, physics, and the deeper nature of reality. And finally, one last question. If humanity ever had to build an artificial universe, would we need to simulate an entire physical world? Or would it be enough to connect and keep the observer's mental models synchronized? And is it possible that our own universe already operates on a similar principle? Let me know what you think in the comments. I'm curious which of these two possibilities you find more convincing.